Let's go ahead and jump into section 4.5. It says we have been talking about all types of triangles and the characteristics that are true about them. Now we will zero in on right triangles as they have some special characteristics and properties. So it says use the diagram to the right to answer the questions. Find the area of each of the squares coming off the sides of the right triangle in diagram 1. Note the areas inside. And students got 9, 16, and 25. It says what seems to be the relationship between the areas. They were able to see that it looked like the two small ones, the areas added up to be the big one. Now it says, what does it seem to indicate about the relationship between the side lengths of a right triangle? It seems like if you square the short side, which we're calling A, a square made off of an A by A, and then we square the other one, a B by B, it is going to fit into the area of the longest side, C by C. Okay, so squaring the small side plus squaring the medium side equals squaring the big side. Now, instead of having actual side lengths, diagram 2 just lists them as A, B, and C. Inside each square, note the area. So it's an A by A, which is an A squared, B by B, which is B squared, and a C by C, which is C squared. So we know that the A squared plus the B squared will equal the C squared. That is called the Pythagorean theorem, and that's what we're going to be working on today. Look at the diagram to the right, diagram 3. Does the triangle have the same property as the ones above? Well, if you look at this, the little one square gets 4, the other one gets 9, and 4 plus 9 is 13, but the big one is 16. So it doesn't seem to work. Does not work. Now, why does it not work? Well, the big difference is that the ones we had been looking at were right triangles, and this is not a right triangle. This is going to be a obtuse triangle. So the Pythagorean theorem does not work for an obtuse triangle. Okay, the next one says the Pythagorean theorem is a biconditional, meaning it is true in both ways. So if the triangle is right, then a squared plus b squared equals c squared, and if a squared plus b squared equals c squared, then you know that it has to be a right triangle. What if they're not equal? So the first question is, what happens if the c squared part was bigger? The only way c squared could get bigger is if c got bigger. Now imagine a right triangle, as I showed here, but c is getting bigger. What do you end up getting? An obtuse triangle. So on this one, you can see that when c gets bigger, the right triangle becomes obtuse. So if you look at a squared plus b squared and it's smaller than c squared, then it is actually going to be an obtuse triangle. Now, what about if a squared plus b squared was the bigger one and c squared got smaller? If you look at a right triangle and c squared got smaller, the only way that's possible is if c got smaller. And if you look at a right triangle where c gets smaller, it is going to be a acute triangle. So the quick notes, as you can see here, are just that the Pythagorean theorem says if the triangle is right, then a squared plus b squared equals c squared. And we could write that as a biconditional also. The triangle is right if and only if a squared plus b squared equals c squared. We talked about if a squared plus b squared equals c squared, then it's right. If the c part got bigger, if you imagine a right triangle where c gets bigger, it becomes obtuse. If you imagine a right triangle where c gets smaller, it's going to be acute. So that is the main things from this lesson. Now, we've looked at some examples of right triangles with actual side lengths. Is it enough to say we have proved the Pythagorean theorem? And the answer is no, because this is just evidence in specific cases, but it does not look at infinitely many cases. So what we're going to do is look at an algebra-based proof here. We're going to do a formal proof of the Pythagorean theorem. I have started the process, finished simplifying both sides. So one way that we do proofs sometimes is a totally different type of proof than what we've looked at before, is you calculate the area in two different ways, and since they are the same exact figure, it better have the same area. So for this figure that we have over here, we can calculate the area as a whole, just one big square that has a side length of a plus b and the other side of a plus b. And you could find out what the area is of that. You could also say that it is going to be 4 triangles and one square that is a c by c. So when you find the area on the left one and you do a plus b times a plus b, you need to remember your skills from Algebra 1, which is foiling. And when you FOIL this, you get a squared plus 2ab plus b squared. If you find the area of the 4 triangles plus the square, the 4 1/2 base times height give you 4 times 1/2 ab, which is 2ab, and the square in the middle is the c by c, so it is 2ab plus c squared. That means the left side must equal the right side because they're both talking about the same exact area. And if we do that, and then we subtract away the 2ab from both sides because they have it in common, you end up with a squared plus b squared equals c squared, which is the Pythagorean theorem. Now on here, students just practiced using the Pythagorean theorem. In A, you have your A and B, you do not have your C. So we did 5 squared plus 12 squared equals x squared. You get it down to the point where it's x squared equals a number, and you square root. And even though it's technically 13 and negative 13 just doesn't make any sense. We don't write it down. The next one, we have the A and the C, but we don't have the B. This is the one that students usually mess up on because they will do 6 squared plus 10 squared equals x squared, and they'll get a number bigger than 10, which just makes no sense. So here you get 6 squared plus x squared equals 10 squared. 36 plus x squared equals 100. When you subtract away the 36, you get x squared equals 64, and when you square root, you end up getting x equals 8. Now, on number 4, we are just trying to figure out, does a squared plus b squared equal c squared? Because if so, it's right. If not, we have to think a little bit and ask, did the c get bigger or did the c get smaller, to find out if it is acute or obtuse. So on the first one, you can see that a squared plus b squared does not equal c squared, that c squared got bigger, which means c got bigger. And if you have a right triangle where c gets bigger, it's going to be obtuse. The next one, a squared plus b squared, does equal c squared, so it's going to be right. And on the next one, the c squared is smaller, which means c got smaller. And the only way c can get smaller is if you got a right triangle and made c get smaller, it would become acute. All right, let's take a look at the homework here. First one says, the Pythagorean theorem can be used for what type of triangles? Only right triangles. Make sure you are careful with that. The next ones, you are just checking, does a squared plus b squared equal c squared? Is c squared bigger or is c squared smaller? And the first one, c squared's bigger, which means it became obtuse. B, they are equal, so it's right. And on the last one, c squared got smaller. And if you look at a right triangle where c gets smaller, it becomes acute. Now, on number 3, you are using the Pythagorean theorem. A, you had A and B, not C, and you could solve. The next one, you had A and C or B and C, and you're solving for the other. This is the one that people usually mess up on. And this is a special case where you technically don't need to have 2 of the sides of a right triangle. You only need to have 1 of them, and you can still solve. So it's x squared plus the other side, which is x squared, equals 10 squared. 2x squared equals 100. X squared equals 50. And you get about 7.1. The next one is a 20-foot ladder leaning up against a building. The bottom of the ladder is resting 5 feet from the building. How high up the building does the ladder reach? Draw a basic picture. So we have that slanty part being 20. The base is 5 feet away, and we're trying to figure out how high it goes. That's x. So you have a right triangle, and you have the A and C, or the B and C, depending on what you're calling 5. So you can do the Pythagorean theorem and solve, and you get 19.4 feet. Make sure you don't draw some weird picture of a ladder that's not leaning diagonally or something like that. Why is the following evidence the Pythagorean theorem and not a proof? Because it is a single example where A is 3, B is 4, and C is 5. So that was the issue. And the last one, Kendrick is trying to use the Pythagorean theorem to solve the following sides. His work is shown to explain what his mistake is and explain why he should have known he completed the process wrong. So he looked at this, he did 3 squared plus 4 squared equals c squared, he solved. Well, he messed this up. He called c b, and that threw everything off. And he really should have known that this was wrong because he got an answer that was 5, and the longest side of a right triangle is always the hypotenuse. So it made no sense for the hypotenuse to be 4 and then the other side to be 5. All right, hopefully that made sense. Thanks for watching.